is product of two upper triangular matrix and upper triangular matrix. So first of all, let us look at what is upper triangular matrix. So what you can see in the screen is that the matrix here on the left, it looks like all of the entries below the diagonal entries. So the diagonal entries here are these entries which I have marked in yellow, highlighted, and all of the entries below the diagonal entries, if they are zero, the matrix is upper triangular matrix. So the question here to ask is that when we multiply two upper triangular matrices, do we get back an upper triangular matrix? So let us first of all take examples. So I have opened this some online calculator and I have taken here two matrices which are like upper triangular, and so there are two 3 by 3 matrices, and it turns out when you find the matrix multiplication of these two matrices, you do get back an upper triangular matrix here. So let us take two 4 by 4 matrices, or let us first in fact check whether it works for say 2 by 2 matrices. So the first matrix is this, and let's remove the, and the second matrix which I'll take is say this. Okay, so it looks like both these matrices are upper triangular. So let us see. Let us look at the first two matrices. Yeah, there's missing. Okay, so now we have two by two matrices here. I'm just randomly taking these two matrices. I mean, there's no logic for the entries of the matrix. So these both of these matrices are upper triangular in the sense that everything below the diagonal is zero. So diagonal is 1 and 2 here, and 5 and 5. So the result is also an upper triangular matrix. So let us take example of a 4 by 4 matrix, like say 1, 2, 3, 4. The second row should be some number 5. So this is the second row. Then we have the third row. Let's just say the third row will have two zeros in it, and say, and let us take the fourth row. Yeah, so the fourth row will be say 0, 0, 0, say 7. So this completes writing the first matrix. Just copy it, and so let us look at the, okay, let us say that like the, let us say that, okay, so there's a mistake here. So 1 2 3 4 comma 0 2 4 5 0 0 0 3 4 and 0 0 0 7. So now these two are two upper triangular matrices which are 4 by 4, and of course I took same matrices, and even if I didn't take the same matrix, say I put 100 here and I put say 400 here, and even then, I mean, any two upper triangular matrices you take, you get back a result which is always an upper triangular matrix. So I showed it as true for any 2 by 2 matrices, 3 by 3, 4 by 4. Is it valid for 1 million by 1 million? I mean, so this is such a strong statement that product of two upper triangular matrix is always an upper triangular matrix, and we will try to prove it for any, I mean, for any case. So so let us consider two upper triangular matrices. Say one matrix is A and the second matrix is B. So let us take that they are not of the same dimension. So for example, like if A is m cross n, and so B could be n cross P. I mean, it's just that the matrix multiplication should be possible. So I took some matrix A m cross n, where there are m into n entries, and I took a matrix B. I ensured that this B has n rows and A has n columns. So I'll just take a different color on that. Yeah. So what I mean here is that A has n columns and B has n rows. So that is the condition for the matrix multiplication to be existing. So since we can notice here, can we deduce a formula for what, can we write a neat formula for what is an upper triangular matrix? So let us see what is uh, the sequence of logic followed here. So we see that the A to 1, this position, is 0. So this position is nothing but this A21, and this is 0. And we see that this A31, 32, 32, both, sorry, yeah, A32 and A31, both are, these are 0. So these are the, likewise A41, 42, 43 are 0. And likewise 451, 52, 53, 54 are 0. So what we see here is that when the index I, so this index I here, I'll use a color to denote it, when this index I is greater than the index j, only then the entries are turning out to be 0. For example, when here the index j is 3 and the index I is 1, it is not that the index j is greater. So hence wise it is not 0. Any case, any entry in which the I index is more than the j index is 0. For example, I mean, it is strictly greater than, I mean, the I should be strictly greater than the index j. I mean, why I mentioned strictly is because if it is equal, we are looking at diagonal elements, like the elements of on the diagonal. So the elements on the diagonal are not zero. For the upper triangular matrix, everything below the diagonal is zero. So the definition boils down to Aij is zero whenever I is greater than j. Okay, so having said the definition of upper triangular matrix, let us use it to prove that product of two upper triangular matrices is an upper triangular matrix. So, for example, I took this matrix A and matrix B, and of course, the C has this dimension which is M and P, M cross P. So, how matrix multiplication is defined as that any, so this is the matrix A and this is a matrix B, and I get back output which is the matrix C. So, any general element, so I take C here is Cij. So, we know that Cij sits on the ith row and the jth column. And the way to get Cij is you multiply this entire ith row of the A matrix by an entire column jth column of the B matrix. So it's like AI1 times B1J. A, so this is AI1 times B1J. And so the next entry will be AI2 times B2J. So that's the second entry in the ith column, and the second entry in the, so in second entry in the ith row, and the second entry in the jth column. So likewise and so forth. So Cij is nothing but a, so this thing times this thing time plus this thing times this thing dot 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 this thing times this thing. So this is nothing but the general term of a matrix multiplication. So we can neatly write this in this compactly by using a summation symbol, and we can see here is that it is this index which is getting summed over. Like we can say that it's the, we are moving column wise in the, when we are looking at the jth column, when you're looking at the jth row, we are moving column wise, and when you're looking at the jth column, we are moving, we are indexing and moving uh, the row index. So here this is the entry which is changing from 1 to n. So we just sum this up from summation from 1 to n, a times b kj, where k is the variable. I mean, this k sums up from 1 to till n. So yeah, the summation index runs from 1 to n. And now what can we do? I mean, our entire goal is to show that product of two upper triangular matrix is an upper triangular matrix. So if I show that the general term Cij is 0 when I is greater than j, then my job is done. So what we can do is that we can use a smart trick. So first of all, what we will do is that will split this sum into two parts. So what we will do is that the sum can be seen as two sums. So the first sum is from k is equals to 1 to I minus 1. And so you take the sum till I minus 1, say till here. So everything below is still k is still I minus 1. So this is from k is equals to 1 to I minus 1. And then you take the sum from I to k is equals to n. The same sum, we are just looking it into two parts. I mean, this is the first part of the sum, and this is the, let's say, second part of the sum. So this is the first part and this is the second part. So it's just that this thing will be the same. So let us look at the first part. So the first part is the case where running from I to I minus k is running from 1 to I minus 1. So now let us look at the first term itself, which is ik. So the second entry, which is k is, we know that k runs from k is equals to 1, k is equals to 2 till I minus 1. So at most it can reach I minus 1. So this first entry is always greater than the second entry, and hence the I mean this since A is an upper triangular matrix, this term this term itself is 0. So if this term itself is 0, the I mean every term in this, whatever be the second term, it will be always be 0. So the first term of the C, or the first, we can say that the first partial sum is 0. So this is the first part of the sum. So till here, everything here till is 0. So let us look at the second part of the sum. So let us, the second part of the sum is where from I runs from k runs from I to n. So, and we want, I mean, let us look at the sub case where I is greater than J, because my entire goal is to show that the matrix C, the Cij should be 0 when I is greater than J. So let us look at this second term and let us examine what happens if I is greater than J. So if I is greater than J, let us look at this term. So the second term is Bkj, and we know for a fact that, I mean, since the summation is going from I to n, it's k, the first term in this sequence or the series is with I, the second term is I plus 1 with I plus 1 j, and dot 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 b n j. So since this first entry is always, I mean, since we know that I is greater than j and j is always less than I mean, we can be, I mean, using this and this, we can say that k is always greater than I, k is always greater than j, because of course k is of course greater than or equal to I, right? Because it the minimum position the k can take is I, and it can go till higher, which is like I plus 1, I plus 2, I plus 3. It can go up till max n. So of course k is greater than I, and given that I is always greater than j, no, not equal to, I should use greater than. So given that I is strictly greater than j, it implies that k is strictly greater than j. So since k is greater than j and the first index is greater than the second index, and since we'll borrow the fact that B is also an upper triangular matrix, so hence the second term becomes 0. So if the second term becomes 0, this entire this entire thing, the second component also becomes 0, but we are in the sub fact that only when I is greater than j. So we are almost done. The Cij is nothing but, I mean, we broke the sum into two parts, the first half and the second half. So the first half is always 0 regardless of I is greater than j or j is greater than I, or they are equal. And the second part depends on the condition. Like we only looked half of the condition, that when I is greater than j. And when we look at the Cij is nothing but 0 plus the second term. And the second term is 0 when I is greater than j. And that's what we want to prove also. I mean, we want to prove that Cij is 0 when I is greater than j. We don't care when I is not greater than j, or when I is equal to j, or when I is not I is less than j. When I is less than j, we do not care about those conditions, because the matrix is upper triangular, and we only care. I mean, we do not look at the entries above the diagonal. So this matrix Cij says Cij is equal to 0 when I is greater than j. Hence, I mean, we have proved that for any general case, Cij is 0 when I is greater than j, and hence Cij is an upper triangular matrix. Okay, this proves for the infinite case. I mean, even not even, I mean, any natural number you take, if you take 1000 by 1000 matrix and you multiply it to 1000 by 1000 matrix, you will always get an upper triangle. I mean, when you take multiply two upper triangular matrix, even if they are like 5 by 5, 6 by 6, or 100 by 100, you'll always get a upper triangular matrix. Okay, So given that we have proved this result, what more follows from it? For example, let us look at the corollary that let us take that A is an upper triangular matrix. Then it automatically implies that A square is an upper triangular matrix, because say A square is defined as A times A. So A is upper triangular, A is upper triangular, the product is also upper triangular. Okay, let us look at A cube. A cube is defined as A square times A. So since A square is upper triangular, as we proved in the first part, I mean in this part where we proved that, so this is the part say 1. So in this part 1, we proved that A square is upper triangular. Now I know that A square is upper triangular, A is upper triangular, hence A cube is upper triangular. I'll use this part 2 to prove part 3. So since we now proved that part 2 is true, that means that A square is upper triangular and A is upper triangular, therefore A raised to 4 is upper triangular. And any general case that A raised to n is defined as A raised to n minus 1 times A. When I use the word times, it means matrix multiplication. So is A raised to n minus 1 is true because I, by the same logic, this part n minus 1th term or the nth, that A raised to n minus 1 is an upper triangular matrix. So A raised to n minus 1 is upper triangular, A is upper triangular, hence A raised to n is upper triangular. Okay, let us look at another corollary. So which is that I constructed some function of a matrix. So it makes less sense to put in the domain of a function a matrix, but let us still do it anyway. And so so let us say that if this matrix is this function is defined like this, it's like some constant times the identity matrix. Let us take it as of the same order as so yeah, let us say that it is defined only on so of course a square, yeah, it is defined only on square matrices. So let us say that if A is n cross n, let us take this I is also an n cross n identity matrix. So let us define this f of A as some constant where C1, C2, C3, dot 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 Cn are some constants, say some real numbers or some scalars. So C naught times I plus C1 times A plus C2 times A square we defined earlier here, and dot 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 Cn times An, and likewise we have defined every term. So since for example we proved that this is upper triangular, this is upper triangular, this is upper triangular, and we will use the fact that when we multiply an upper triangular matrix with a constant, it still remains upper triangular matrix. So this result is kind of obvious, and the proof is like, I mean, one line you could prove this, that multiplying an upper triangular matrix by a constant, it always remains an upper triangular matrix. We will use another fact that addition of two upper triangular matrix is an upper triangular matrix, and hence wise like addition of three upper triangular matrices is an upper triangular matrix. So of course addition is a binary operation, you take two of them at a time and you keep adding. So of course like now when you use those two results, we can conclude that this entire f of A is an upper triangular matrix. So yeah, that's it for this